All right, we continue with performance. We are still using the slides from the book Computer Networking, a top-down approach. So we are going to talk about performance, loss, delay, throughput. So let's start. How do packet delay and loss occur? Packets queue in router buffers, as we mentioned before, waiting for their turn for transmission. Queue length grows when arrival rate to link exceeds output link capacity. Packet loss occurs when memory to hold queued packets fills up. Okay, so these are packets being transmitted, and these are packets in the buffer queuing delay. Of course, with new devices, the buffers are increasing and so on, but if this speed is higher than this one for a long time, regardless of your buffer size, some packets will be lost anyway. All right, so there are 4 sources for packet delay. Let's talk about them. Of course, all of these delays ends up with the total delay for the nodes. So we're currently talking about a single router, but of course, there will be n routers at the end. So let's start with the delay occurring at a single router. Okay. So these 4 sources are nodal processing, queuing, transmission, and propagation. And let's start with nodal processing. So the packet is received. So the host sends it to the router receives it. So there's some processing, which is checking bit errors. So there's actually coding theory involved. So you don't simply send only your data. You also send some redundant bits, which allows you to check errors. So if you can correct, so if there are only a few bit errors, you can correct this. But if there are a lot of errors, you can detect it, but not correct it. So you have to ask for retransmission. Okay. And also another processing is that since this packet has a destination, you check your table and determine which output link you are going to use. We said that this is about routing algorithms. And this is really fast and becomes faster and faster because we have better devices with better computational power. So typically, this takes microseconds, which you shouldn't feel. The second thing is that queuing delay. Time wasting at output link for transmission depends on congestion level of router. So if there is any queue, there is no queuing delay. But if there are a lot of packets transmitted, there is a burst of data from all of the hosts, then queuing delay might be milliseconds, sometimes seconds. And if it becomes minutes, then packet loss occur. So the third thing is transmission. We mentioned this before. L is your packet length, and this link actually allows R-bit transmission rate, right? So you have to wait L over R seconds. So if L is small, then this is really small. So the final thing is propagation delay. So this is the time taken from sending this packet to here. So this is actually about the physical thing. So sometimes people cannot see the difference between transmission delay and the propagation delay. So here the propagation is physically sending this packet from here to here. So the length of this cable or the distance actually determines your propagation delay. So D is the length of physical link. S is the propagation speed, which is close to speed of light. So the propagation delay is D over S. So as you can see, problems might occur at the queuing delay and sometimes at transmission delay if your links are bad. But nowadays, due to technology, we have really good links. We have very capable fiber optic cables, and most of the time we are not, using them at full capacity. So queuing delay is most of the time what you see. Yes. Here's a caravan analogy. So try to explain how it works. So there's a 10 car as a caravan, so we can think them as 10-bit packets. So there's a toll booth, so it allows one car at a time. So until the toll, you travel as a group, but here you have to go one by one. And the toll booth actually performs some operations, so you have to wait in the queue. So in this example, let's say that there is a 100-kilometer distance between toll booths, and toll booth takes 12 seconds to service car. So you can think this as a bit transmission time. Propagate at 100 kilometer per hour. So how long until caravan is lined up before the second toll booth? So idea is as follows. When the service takes 12 seconds, but after the service is ended, this car instantly reaches 1 kilometer per hour speed and travels this distance. So question is how long it will take for these 10 cars to queue here. Right? So in this example, time to push entire caravan through toll booth onto the highway is 12 seconds times 10 because there are 10 cars, processing takes 12 seconds. So after 2 minutes, 120 seconds, the last car will leave this toll booth. But time for last car to propagate from first to second toll booth is since, all of the cars travel at 100 kilometers per hour, and this distance is 100 kilometers, so it will take 1 hour for a car from here to travel. So this propagation delay is 1 hour, and this part is 2 minutes. So in total, it will take 62 minutes for all of the 10 cars to leave this toll booth and reach here. So as you can see, here the problem was the propagation delay, not the toll booth, because toll booth actually served in 2 minutes, but the distance was long, so it take 1 hour for these cars to travel to here. So in total, you spent 60 plus 2 minutes, so 62 minutes. So let's modify the example. So assume that now cars are, sport cars. So assume that physically, I don't think it's possible, but assume that they can reach 100,000 kilometers per hour. I mean, it will burn their tires, but anyway, so assume that they are now a lot faster. So suppose toll booth now takes 1 minute to service a car. So, cars are faster, but the person working at the toll booth is now slower. So will cars arrive to second booth before all cars service at the first booth? Question is as follows. And the answer is yes. After 7 minutes, first car arrives at second booth, 3 cars still at the first booth. So you might think why this is the case. So here, for the first car, it will take 1 minute, due to our example. But since it travels 1,000 kilometers per hour, it will take 6 minutes to travel here. So at the 7th minute, the first car reaches here. But at the 7th minute, there will be still 3 cars waiting for to be serviced. So as you can see, this transmission delay and propagation delay are completely different things. And, the delay might be caused by something else. In this first example, delay was from this propagation delay because cars were slow. In the second example, cars were fast, but the toll booth was slower, so it take a lot, still more than 10 minutes to this car to leave here and travel there. So I think in this example it will take 16 minutes or something for all of the cars to reach the second booth. Okay. So let's revisit packet queuing delay. So we're retalking it because we said that in general it requires L over R, but we don't know at which frequency packets arrive. So here we add another variable saying A, average packet arrival rate. Okay. So this time the formula is now we multiply it with A. Arrival rate of bits divided by service rate of bits actually determines your traffic intensity. So if average packet arrival rate is really huge, for instance, if this services were given to 100 customers, and if all of the customers, for instance, create a burst of data, A will increase a lot. So A times L will be a lot larger than R, which will cause a problem. So let's look at it in this way. If L times A divided by R is close to 0, this means that there isn't any queuing delay at all. No, I mean, it is negligible because anything comes directly, transmitted. But if it is close to 1, this means that the average queuing delay is really large. But if it is larger than 1, more work arriving is more than that can be serviced. So average delay becomes now infinite, so packet drops will occur. So here's actually a graph showing you how it works. So this is the traffic intensity, L times A divided by R. So if it is less than 1, the queuing delay is small, but at some point on, it increases exponentially, right? So when it comes close to 1, queuing delays increases a lot. So, and another analogy is as follows. Assume that you are in a Istanbul traffic, which is always slow. There are a lot of queuing delay, but so assume that you are at this point, but something unexpected happens. For instance, if it rains or a car crash occurs, you feel that kind of exponentially. It's such a small event, creates a lot of delay. So here's the analogy also with pictures. So real internet delays and routes. What do real internet delay and loss look like? Traceroute program provides delay measurement from source to router along end-to-end internet path towards destination for all I. So for all I, sends 3 packets that will reach router I on path towards destination with time to leave field value of I. Router I will return packets to sender. Sender measures time interval between transmission and reply. So assume that there are 20 routers between the source and the destination. So you will send 20 times 3, in other words, 60 probes, just measuring, so you send these special packets to the routers, and routers answers you back. So you measure how many milliseconds it took from you sending the message and receiving it back. So this is also explained in RFCs. So this is why traceroutes works in different operating systems. For instance, last time we used Windows, and I think the command was trace RT. So you can just write trace RT and then the domain name, and you can check how long it takes for these probes to go and come back. So again, here's an example from the book slides. So here they are testing the traceroute from the university in United States to visit Eurocom in France. So as you can see, there are 3 measurements because we are sending 3 probes. So delay three delay measurements. Of course, inside the campus in this university, the delay is really small. You instantly heard from your router, but after some point on, you will leave your ISP, and here, as you can see, 2-digit milliseconds turns into 3-digit milliseconds. This is because transoceanic link. So here you are leaving United States and moving on to Europe through a fiber optic cable below the ocean. This is why it increases. And as you can see, of course, since the next router is further away, so these numbers are always increasing. And here something weird happens, because at the 10th router, your measurements was larger than 113 milliseconds, but for the 11th router, you hear something less than these values. So for some reason, this 10th router answers you, in a longer time, but this answers in a shorter period. The question is why? Of course, we can talk about it, but let me give you the quick answer. This is due to queuing delay. So at this, because it depends on time. For instance, at this probe, maybe there were more queues, so it takes longer for this router to answer you. But in the next probe, there wasn't much queue, so this is why you heard it, faster. Okay. As you can see, sometimes you will see stars here. So you send 3 probes. If at least one of them does not come back, so it is lost, then the trace route actually will show you 3 stars like this. So this might be due to the reason router not replying. Maybe they, configured that way so that's, to avoid denial of service attacks, they don't answer you back. Or sometimes they just check, how many hops this probe made. So if it is coming from a, distant computer, they may choose to not to respond you back. So regardless of that, you didn't hear it back. So this is why sometimes you don't see any measurements. Okay. Packet loss. Q, also known as buffer preceding link in buffer, has finite capacity. So you cannot have infinite memory, right? This has to be finite. So when it is filled, generally newcomers are dropped. But of course, you can configure the router to drop the waiting ones. But of course, it wouldn't change the thing that we will have packet loss at the end. So packet arriving the full queue dropped, also known as lost. Lost packet may be retransmitted by previous node, by source and system, or not at all. So we will talk about TCP and UDP. And in the TCP case, we will resubmit it. But in the UDP case, we will not know it if it is received or not. So let's talk about throughputs, because we are talking about performance. So throughput rate bits per time unit at which bits are being sent from sender to receiver. Instantaneous rate at given point in time, average rate over longer period of time. So this is what we do, when we are measuring our internet speeds and so on. So here's an example. Here's a server with file of F bits to send to client. And there's a link here from server to router. This link capacity is RS bits per second. From this router to your host, link capacity is RC bits per second. So question is, how long will it take for this file to reach here? So what will be your transmission rate, your throughput? So there's a pipe analogy here. So think this file as a, some kind of fluid. So there's a pipe here and also another pipe here. So you're actually transmitting this fluid from these 2 pipes. So here what they are trying to show is that one pipe might be, larger than the other, but your speed is determined by the smaller one, right? Because this can be, large, this pipe, but, it will take longer for it to travel through this pipe. So if RS is less than RC, what is the average end-to-end throughput? The answer is RS, because it is smaller. And for the case of RS being larger than RC, then your average end-to-end throughput will become now RC, because it is the smaller one. So bottleneck link is the link on end-to-end paths that constrains end-to-end throughput. So this is actually what happens. For instance, in Turkey, the connection speeds were really low for a very long time. So it doesn't matter the rest of the world, because they had RS as large. But the service you bought maybe was just 8 megabits per second. So this is actually the top speed that you can reach. So your bottleneck actually determined with this link. Okay. So let's think about the network scenario. We have, in this example, 10 connections, and they fairly share backbone bottleneck link R, bits per second. So per connection end-to-end throughput, minimum of RC, RS, and R divided by 10. So the minimum of this value actually determines your connection speed, because think about it in this way: if not the other 9 computers are using the network, you can use the whole R, right? But if RC is smaller than R, it doesn't matter you are using this R, because your speed is bottleneck with this RC. So in practice, RC or RS is often bottleneck because we have very good and high capacity fiber optic cables between hosts. So this concludes our discussion of performance. We will continue with security.